Okay, good afternoon, Michael, Chazelle, Jeanette, Jonathan, John Christian, Noriel, and Denmark. So we have a lot of things to cover today. So probably I'll start right away with minimal kwento na lang on the sides sa araw na ito. Ano? But first, I just made an update on Module 8 that was uploaded in Canvas. So before you do the exercise, kindly make sure to download the latest version. Kasi meron akong mga typos dun sa formula. Although, kung susundan mo yung discussion, mag-make sense pa rin siya. Pero I needed to adjust the notations to make it more conventional. Kasi yung ibang formula so ibang mga bagay na sinulat ko last time, specifically regarding the two norm, ay medyo from memory. Tapos nung kinonsult ko yung reference ko dun sa methods natin today, medyo magkaiba pala kami ng conventions, all right? So kaya kailangan kong i-adjust yung notations from the previous version of Module 8. Tapos dun na rin sa latest version ng Module 8, natapos ko na yung discussion about the Gauss-Seidel and the SOR method na wala pa dun sa version as of Wednesday last Wednesday. Tapos actually nag-upload ako kagabi. Kung nag-download kayo kagabi, may bago uling version. Siguro mga around 11:03 kanina because I realized there are still some wrong values that I need to correct. So, ngayon meron ng final, punta kayo kay Canvas, i-download niyo siya bago kayo gumawa ng problem set, okay? So the main correction that I had to implement to the module is my definition of the two norm, all right? So yung two norm ay sabi ko last time it's the square root of the of rho of A, and I call rho of A the largest eigenvalue of A transpose A. So ito yung sinabi ko last time na kailangan kong i-check kasi yung rho of A dun sa reference na ginamit ko kay para sa discussion natin today, this is called the spectral radius and it is defined to be the largest eigenvalue of A. Hindi siya yung largest value ng A transpose A, all right? So let me correct that. The spectral radius of a matrix A is its largest eigenvalue in terms of absolute value. So it's the largest, siguro largest in magnitude. Yan tuloy, meron pa uli ako nakita correction. It's the largest in magnitude. So kunin mo yung lahat ng eigenvalues ni A, tapos ipa-compute mo at pa-compare mo yung kanilang mga absolute values. Yung may pinakamalaking absolute value, siya yung tinatawag natin na spectral radius ni matrix A. Alright? Now, kailangan siyang makorek kasi ang spectral radius ng isang matrix, tama nga ba? Yeah, so okay na to. So siya yung largest in magnitude na eigenvalue ni A. Tapos yung two norm ng isang matrix is the square root of the spectral radius of the product of A transpose A. Kaya yung calculations last time in the examples ay totoo pa rin kasi na-define ko doon yung spectral radius to be the largest eigenvalue of A transpose A. Tapos ang kinunan ko na lamang ng square root ay yung rho of A, where rho of A actually is the largest eigenvalue of A transpose A. So basically, this is this definition is equivalent to what I wrote last time, pero para maging consistent siya all throughout the module. So yung rho of A, siya na talaga yung spectral radius, which is the largest eigenvalue of A in terms of magnitude. Tapos yung two norm is the spectral radius, is the square root of the spectral radius of the matrix A transpose times A. All right? But actually, hindi natin ko-computein yan mano-mano kasi una, kailangan matuto tayong paano mag-compute ng eigenvalue, which is tackled in linear algebra courses. And actually, for large matrices, computing the eigenvalues are quite difficult. All right? So kaya kung nagba-MATLAB kayo, gagamitin nyo lang naman dyan ay norm ni A, 2 to get the two norm of the matrix A. So hindi nyo na kailangan computein yung eigenvalue, yung spectral radius, and so on. Automatic nyo nang ibibigay. I'm not familiar with Python, pero search nyo na lang paano mag-two norm kay Python. Kay Mathematica, norm of A, 2 Yan naman yung syntax where A is declared as a matrix. So hindi rin kayo mahirapan. So usually programming languages have an intrinsic routine to compute the norms of the matrix. Usually the P norms where P is equal to 1, 2, and infinity. So ito yung 1, 2, at saka infinity norms ng isang matrix o dili kaya ay isang vector. Okay? So please correct that or at least download the latest version. But I guess all of the calculations still apply. Okay. So para makadiretso na ako ngayon sa iterative methods in solving linear systems na medyo nasimulan ko na last time. And again, remember our problem is to solve the system AX equals B, where A is an n by n matrix, X is an n by 1 matrix, and B or an n vector, and B is another n vector. All right. Tapos sabi natin, pwede ko itong tingnan as a root finding problem. That means finding the root x of the vector ax minus b. All right. And then if you're talking about root finding, susunod na papasok sa isip mo, baka pwede tayong mag-fixed point iteration. All right. And I mentioned to you that the idea that we will be working on today would be creating a fixed point iteration for the equation, for equation 8.1. Okay, hanapan natin ng roots yung ax minus b, all right, using a fixed point iteration. So the first step is actually to transpose the system ax equals b into an iterative scheme such that that iterative scheme, or actually strictly, will be finding the fixed point of the vector tx plus c. All right? So gusto nating maging equivalent yan. Yung solution x ng equation 8.1 ay siya rin yung fixed point ng right-hand side ng 8.2. So yun yung gusto natin gawin. Pero bago natin hanapin ano dapat yung matrix T, which we call to be the iteration matrix, at ano yung translating vector C, kailangan muna natin pag-usapan yung convergence ng fixed point iteration o nung formula 8.2, nung equation 8.2 into a root of equation 8.1. So yun yung mga unang questions na gusto nating sagutin. And I think I posed 4 questions towards the end of the lecture last time. So sagutin natin sila briefly. Tapos para makilala na natin ano yung mga iterative methods na kailangan yung i-implement in the laboratory exercise on Monday. Okay? So again, pag meron ka ng x plus, pag na-translate na natin yung linear system into a fixed point iteration, into a fixed point problem, x equals tx plus c, we can define the fixed point iteration this way. All right. So we got x upper k plus 1. So yung upper subscript, di pala upper subscript, yung superscript, siya yung nagsasabi nasa pang ilang iteration na tayo. Kasi yung subscript usually ginagamit natin para dun sa pang ilang component siya ng vector. So ngayon kailangan gumamit ako ng subscript. So you have the fixed point problem, x equals tx plus c. Then we want to develop a fixed point iteration for that. That is the k plus 1 estimate for the fixed point x will be equal to the iteration matrix T times the previous estimate x upper k plus the translating vector c. And we need the starting condition x upper 0 kung saan magsisimula yung sequence natin of estimates. Okay? And that's why we say here that it's natural that we call T the iteration matrix because essentially yung pagbabago, yung pag-update ng iterates ay nakadepende doon sa matrix T. Okay? And then we devoted last time or our discussion last time into meeting how to measure the size of vectors and matrices kasi kailangan natin ng stopping criterion dito. Okay? So specifically, we can use a relative jump-based stopping criterion. Okay? I-measure natin gaano kalapit yung dalawang estimates or the last two estimates from each other. If there is no significant jump from one iterate to another, then we can stop our iteration. So in particular, of your choice of norm, pwede nating i-measure yung size ng x upper k plus 1 minus x upper k all over the norm of x upper k. So gumagamit ako ng relative difference palagi para alam ko na ang epsilon dapat ay percentage error. Okay? So para mas para independent siya dun sa size, or hindi pala independent, para nakadepende siya dun sa size nung x upper k. May tanong si Ezekiel, ano yung significance ni vector c sa formula po? Si vector c ay constant vector. So essentially tinatranslate niya yung previous estimate. Okay? Pero hindi kasi siya directly related kay x upper k. Kaya hindi ko siya tinatawag na transition vector o na iteration vector. Kasi parang ang nangyayari lang, yung pagde-determine ng bagong estimate ay talagang nakadepende dun sa matrix T times yung previous vector estimate. Tapos ita-translate lang siya kasi remember, parang linear system lang siya. Yung ina-add mo na constant, siya yung parang nagta-translate pataas or pababa ng graph ng isang function. Kaya tinatawag ko na lang siyang translating vector. Okay? Kasi makita nyo mamaya necessary na dun sa mga techniques natin gagawin na si C ay non-zero vector. So parang i-adjust niya yung yung product ng iteration matrix times x upper k. Probably it would be easier to see kung ano yung nagiging action ni C o ano yung role ni C dun sa actual fixed point iteration when we consider specific iterative schemes. Okay? Now going back to the stopping criterion, so i-measure nyo lang yan. And since I didn't specify any vector norm, so pwede kayong pumili ng kahit anong vector norm. And since we are doing or we are solving linear systems in finite dimensions, meron tayong equivalence property na nakita natin last time, na lahat ng norms sa isang finite dimensional vector space ay equivalent. So meaning kapag meron kang dalawang norms, napakaganda ng relationship nila kasi yung isa sa kanilang dalawa or alinman sa kanilang dalawa ay bounded below by a multiple of the other vector norm and bounded above by another multiple of the vector norm. So actually it doesn't really matter too much kung ano yung norm na pipiliin nyo. So bahala kayong pumili ng kahit anong norm, L infinity, L1 o kaya L2 norm. Yun yung mga usual options natin. Okay? So, yeah, that equivalence tells us na, okay, pag nag-converge yung iteration with respect to one norm, magko-converge din siya sa iba pang klaseng norms dun sa vector space natin. Okay? So, the main question really is the convergence of the iterative scheme. Kailan nagiging actually, dalawang bagay pala yung main questions. Una, kailan nagko-converge yung iterative scheme? At saka pangalawa, paano natin mahanap si T at saka si C? All right? Let's address the first question first. When is the iteration convergent? Now, okay, babalik tayo dun sa formula 8.2 at yung fixed point problem. I will subtract Tx from both sides of the equation. We'll get this guy, all right? And then I can use the distributive property of matrix multiplication. So I can factor out sort of the vector x. All right. So remember, pag nag-factor out ako dito ng x, hindi 1 yung matitira kasi ang identity rito ay yung identity matrix, right? So pwede mo itong tingnan as the identity n by n matrix times the vector x. So pag finactor out mo si x, makukuha mo ay the matrix I minus t times the vector x is equal to c. All right? Then we can have a solution x to this iterative scheme if and only if I minus t is non-singular. Okay, so magkakaroon ng unique solution itong fixed point problem kapag ka nag-exist yung inverse ni I minus t. And in particular, there will be a unique solution to the fixed point iteration if and only if I minus t inverse is non-singular, and specifically the solution is going to be I minus t inverse times c. So ito yung titingnan natin. Kasi bago ka makapag-guarantee ng convergence, kailangan may solution muna yung fixed point iteration. So now, our idea here is that, okay, dapat ito ay dapat magkaroon ng solution yung fixed point iteration, and the necessary and sufficient condition for that to occur is the non-singularity ng I minus t. And linear algebra tools tells us na yung I minus t ay non-singular if and only if the spectral radius of t is less than 1. Okay? So yun yung condition. Yun yung dapat nating i-check. Okay? So kapag ka nagbubuo tayo ng isang fixed point iteration, kailangan natin yung iteration matrix T, kailangan ko yung translating vector C. Napakahalaga nung iteration matrix. Siguro this is partly to answer Ezekiel's question also kanina. Bakit masyado nagfo-focus kay iteration matrix at hindi kay vector C? Kasi si iteration matrix talaga yung nagsasabi kung kailan may unique solution, yung fixed point problem, at kailan magko-converge yung fixed point iteration. In fact, we have seen in our analysis here that there would be a unique solution to the fixed point problem if and only if the spectral radius of the transition matrix or the iteration matrix is less than 1. Okay. Tapos I will present to you without proof. So sorry ulit sa mga mahilig sa proofs, all right? A sufficient condition, or actually it's a necessary and sufficient condition for the convergence of the fixed point iteration. So kung bumuo ka ng fixed point iteration of the form 8.4, so ang iteration matrix mo ay T, tapos ang CC mo ay, tapos CC ay vector of appropriate size, which and we designed this fixed point iteration to correspond to the solution of the linear system AX equals B, then magko-converge yung fixed point iteration in equation 8.4 into the unique solution of the linear system AX equals B for any choice. Ito pa yung maganda. Kahit ano yung starting vector, if and only if the spectral radius of the iteration matrix is less than 1. So nakikita nyo yung pagiging central nung iteration matrix dun sa fixed point iteration. Kasi kapag yung spectral radius nung transition matrix o nung iteration matrix ay less than 1, sure ka na merong unique solution, yung fixed point iteration. Tapos magko-converge yung fixed point iteration dun sa solution na yon, at hindi lamang yon, the added bonus is magko-converge siya kahit ano pa yung initial vector na mapili mo. Okay? Of course, you want to have an initial vector that is as close as possible to the actual solution kasi because of the following error estimates. Okay? Now again, you will see in the following formula that independent ito ng pagpili ng vector norm o ng matrix norm. So yeah, it depends on the norm that you are using. So usual choices, again, ay yung L1, L2, saka L infinity norm. Yes, nice observation, Benedict. Na sa contraction mapping theorem, ano nga yung binabound natin by 1? It's the derivative of the iteration function. Tama, no? So gusto natin yung absolute value ng derivative ng iteration function natin to be less than 1. So nakikita niyo yung parallel sa fixed point theory at saka dito sa linear system. Because talagang in-extend lang natin yung konsepto ng one-dimensional problem, all right, into multiple dimensions. And that's the usual case. Kaya I'm thinking na sana magkaroon tayo, at least in the math and the BS math curriculum, ng mas malalim na pagtingin sa vector calculus. Kasi pagka nag-work na kayo into higher level optimizations or are actually working on bigger problems, hindi lang equations kasi yung pinaglalaruan natin. Yung mga models natin, usually multiple dimensions yan kasi maraming variables ang involved. So hindi lang tayo nagko-consider ng functions na nag-admit ng multiple variables tas nag-output ng isang real number, pero usually yung sa applications, meron kang isang function na maraming variables, tas ang function value ay isang vector o isang matrix. So dapat matutunan din natin kung paano mag-differentiate ng vectors at saka ng matrices. Alright? Tapos hindi naman kasi ganun malaki yung diferensya kasi nga, halimbawa, napansin nga ni David na kamukhang-kamukha ng contraction mapping theorem, etong theorem 8.2. So the condition, instead of the derivative of the iteration function, ang tinitingnan natin dito ay yung spectral radius ng iteration matrix. Okay? Now, with those in mind, kapag ka nag-hold yung premises ng theorem na ito, so we know that the error on the k plus 1 iteration has magnitude that is bounded above by the operator norm of the transition matrix times the vector norm of the previous error vector. Okay. Define ko ba yung error vector? Sorry, I forgot to define what the error vector is. The error vector, so mag-update na naman pala ako mamaya. The error vector is e to the upper k basically is, sorry, define natin to this way. I equals vector x upper k plus 1 minus x upper k. Right? So ito lang yung difference between two consecutive estimates. So yung error vector upper k plus 1 ay k plus 1 estimate minus the k estimate. Alright, so yan yung error vector. So ang size ng error vector on the k plus 1 iterate is a multiple of the error on the kth iteration scaled by the transition by the norm of the iteration matrix. Okay? Then may gusto bang sabihin nito? Yeah, okay na yan. And then, and you will notice that, okay, ating kamukhang-kamukha naman ito, sir, nung para sa asymptotic error constant natin. Okay? So, but because, actually, sabihin ko ba yan ngayon? And then, later na lang. Ina-note ko na lang para hindi ko siya kailangang i-prove. Alright? And then, if you're sure that the operator norm of the matrix T is less than 1, then makikita natin na yung error on the kth estimate or on the kth iteration is actually just a multiple of the error on the first iteration. Kaya ito yung nagsasabi sa atin na mas maganda kung mag-start ka na mas malapit kung mag-start ka sa initial vector na mas malapit dun sa actual solution. Kasi yung error on any iteration is a multiple of the error on the first iteration. Of course, the scaling is a power of the operator norm of k all over 1 minus the operator norm of t. Okay? So take note of this error bound. So baka lumabas sa susunod natin na problem set. Siguro dun sa objective part. So paglalaruan ko itong mga equations na to. All right. Now, okay. So, nagko-converge yung fixed point iteration kapag yung spectral radius ay less than 1. And actually, this equation over here, the error estimate, gives us a bound for the asymptotic error constant. So kung mapapansin nyo, kamukhang-kamukha ito ng formula ng asymptotic error constant. Yun nga lang, wala na ako nilagay dito na denominator. But actually, it can be shown that this is divided by or actually when you divide this, all right, by the magnitude of the vector e upper k, magkakaroon ka lang ng this guy over this guy. So that's going to be the ratio between two consecutive errors, and that is bounded above by the operator norm of t. So that tells us that this fixed point iteration has a linear convergence. Kasi ang power ng denominator dito ay equal kay 1. And that's not a big surprise because para kamukhang-kamukha ito ng fixed point iteration, and fixed point iterations have linear convergence. So ganun din dito, medyo mabagal, linear din yung convergence. Kaya later makakita tayo ng mga methods kung paano mas mapabilis yung pinaka-basic na iteration method na ating titingnan. And then from this error estimate, we also see na hindi lamang linear yung convergence, ngunit yung asymptotic error constant ay bounded above by the operator norm of the iteration matrix. So napaka-central ng iteration matrix. So we need to be careful on how to select the iteration matrix T. Because the choice of the iteration matrix T is not unique. All right? So maraming paraan paano mapili si T. Pero ano yung babantayan natin? Dapat ang spectral radius niya ni 1, and as much as possible, its operator norm should be closer to 0 para naman mas mabilis mas mababa yung asymptotic error constant, okay? So ibig sabihin, mas mabilis yung convergence. Though, ano nga lang talaga siya, linear lang talaga yung kayang convergence ng fixed point iterations natin o ng iterative schemes na i-discuss natin. Okay? So take note of those numbers. Okay. All right, so any questions so far? Ang bilis, naka 25 minutes na kagad tayo, introduction pa lang. Malamang mangungutang na naman ako ng oras sa inyo. So sorry about that. Sorry in advance, guys. Okay. Now, okay. So yun na yung convergence. Sasagot na natin yung convergence. Ano? Ang susunod na tanong, edi sir, ang problema natin ngayon, paano natin hahanapin yung iteration matrix T at yung translating vector C? Kasi they are crucial in the design of the fixed point iteration. And as I mentioned, there are several ways to do that. Ngayon, isang method lang yung i-discuss ko sa inyo at yun yung tinatawag na mga splitting methods. Okay? Tatlong splitting methods yung i-consider natin. Pero what do we mean when we say splitting of a matrix? So if you have an n by n matrix, we call the pair m comma n to be a splitting of a matrix of the matrix A if A can be written as m minus n, where the minuend matrix M is non-singular. Kaya siya tinawag na splitting kasi hinahati mo or parang pinaghihiwalay mo or sinusulat mo into two parts yung matrix A in terms of a subtraction. So you want it to be written as the difference of a non-singular matrix minus a matrix N. So of course, A, M, and N must be of the same dimensions. So parang ang ginagawa natin dito ay tinatanggal natin, so to speak, to some extent, yung mga entries kay M o yung mga extra dun sa mga entries ni M na nagko-cause ng pagiging singular niya. Alright? Kasi gusto natin makapag-isolate ng isang non-singular portion nung kay matrix A. Okay? And then I remember seeing this in my 175. May dekada na ba nakakaraan? Yeah. So, tanda ko na pala. So, nung nag-175 kami, tinuro yan sa amin ni Sir, sino ba teacher ko dito? Si Sir Atan ang teacher ko rito. Tapos, so several decades passed. And then when I was mentoring one student, parang 3 years ago in the US, meron kaming isang problem. Tapos, kailangan ko ng isang method paano ma-solve yung ODE kasi yun, pero linear system yung solution. Okay? Hindi ko siya ma-solve kasi hindi invertible yung matrix. But luckily, I remember that 10 years ago, tinuruan kami ni Sir Atan ng splitting method na pwede kong hatiin yung isang matrix into two parts. A non-singular part minus another matrix. So, yung pagkaka-split ng matrix na na-isolate ko, yung yung nagko-cause ng singularity allowed us to solve this system of equations that models a spring mass system. So actually, ang laking tulong nun. So yun yung parang mga little snippets, little tools along the way na hindi talaga natin ginagamit directly, pero yung mga natututunan nating techniques na gagamit natin sila in some form or another. Okay? So yun lang yung requirement sa splitting. And obviously, the splitting of a matrix A is not unique. So napakaraming paraan paano ma-split yung matrix M. Ang kailangan mo lang yung matrix A. Ang requirement lang kasi napakagaan. Dapat yung minuend ay invertible. Tapos wala na tayong problema kung sino si N. Siya yung natitira out of the matrix A. Okay? Now, so how does splitting works in relation to translating the system AX equals B into a fixed point iteration? Well, okay, so kung meron kang AX equals B, tapos nag-consider ka ng isang splitting ni matrix A, so si A dito pwede mong palitan ng M minus N. And then we will use the distributive property of matrix vector multiplication. So this is going to be M times X minus N times X equals B. So make sure you have the right ordering in the matrix multiplications, all right? And then I will add nx to both sides to ultimately get mx equals nx plus b. And then this is the reason why we want m to be non-singular, because now we can multiply both sides by the inverse of m and get this guy. And then I will perform the distributive property again. So I will distribute M inverse into the sum nx equals b and get the equation you see in 8.5a, right? So sinasuggest ni so tapos i-compare natin to dun sa fixed point formula. So remember our fixed point formula or our fixed point problem is this. Okay? X equals tx plus c. So ngayon, yung equation 8.5a suggests that we take t to be essentially this guy. Our iteration matrix will be M inverse times N, and our translating vector to be M inverse B. And that's what we have in 8.5b. Okay, and again, the type of method that you get will rely on your choice of the splitting M comma N. All right? And the only requirement is that, of course, M should be invertible kasi kung hindi siya invertible, hindi mo mako-compute si T kasi hindi mag-exist si M inverse. But going through the convergence analysis, aside from M being invertible, we want the spectral radius of M inverse times N to be less than 1. Okay? So yung magre-result na iteration scheme is what we call a splitting method for solving the linear system. Okay? So mukhang straightforward naman, no? So ngayon, ang titingnan natin, magpapakita ako sa inyo ng tatlong distinct na paraan kung paano piliin si M at saka si N. Kasi pag napili mo na yung splitting M comma N, mako-compute mo na si T at saka si C using 8.5b. Right? And then lagi lang nating i-double check or gusto natin na yung spectral radius ni T dapat less than 1 para mag-converge yung iterative scheme. Okay? So we have 3 methods on our plate right now. So ready na ba tayo para tingnan yun? Questions about splitting? Hopefully wala. Napaka-straightforward ng derivation. So hopefully nakikita nyo yung sense para makapag-design kayo later ng mga sarili nyong methods. Okay? So may tatlong methods. Umpisa natin sa Jacobi method. So yung Jacobi method ay, syempre, split natin yung matrix A. Paano ko i-split yung matrix A? Actually, dito naka-angkla dito naka-angkla yung dalawa pang methods. They will be improvements of the Jacobi method. But we will do the splitting of the matrix A through a decomposition of the matrix A into its diagonal, its lower triangular, and its upper triangular parts. So isulat ko muna si A to be D minus L minus U. Disclaimer lang, C has nothing to do with the LU factorization. All right? Ano si D, ano si L, at saka si U? So di ba meron kang matrix A, marami yung laman. Okay? So marami raw yung laman. Si matrix D, siya lang yung diagonal part. So D is the diagonal matrix. 0 siya sa labas ng main diagonal. So ang may entry lang ay si 11, si 22, si 33, si 44, si 55, si 66. Sila lang yung posibleng magkaroon ng non-zero entries. All entries outside of the main diagonal should be equal to 0. And then si L, siya naman yung lower triangular part. Wherein the diagonal will be all zeros. Okay? Tapos 0 rin to kasi dapat lower triangular siya. Tapos nandito yung mga components o yung mga entries na non-zero. Okay? So yun yung lower triangular part ni matrix A. Then si matrix U, siya naman yung upper triangular part. So magiging 0 siya sa diagonal. Tapos 0 siya sa ilalim ng main diagonal. Tapos yung mga non-zero entries nandito siya sa taas. So ganun natin siya dinidecompose. Kunin mo yung diagonal entries, tapos 0 yan sa lahat, Tapos yung lower triangular matrix, kaya lang naka-negative yan, so mind the signs. Kukunin mo lang yung lower triangular part, 0 sa diagonal, 0 sa taas ng diagonal, tapos kunin mo yung negative ng mga entries ni A, siya yung ipaglalagay mo dun sa ilalim ng main diagonal. An analogous principle can be applied to the matrix U. Okay? So I'll give you a specific example later, but that's the idea of 8.6. The diagonal, the lower triangular, and the upper triangular parts. Okay. Now, sir, okay, kung ganyan mo siya gagawin, paano natin kukunin yung splitting M, N? For the Jacobi method, Si M pipiliin ko ay yung diagonal matrix. Because that's easy. It's easy to guarantee that the diagonal matrix or the diagonal matrix is invertible. Linear algebra will teach us na ang isang diagonal matrix, again, ang may non-zero entries lang dito ay yung main diagonal, ay magiging invertible if and only if walang zero dun sa diagonal. And actually, the inverse of a diagonal matrix is the diagonal matrix whose entries are the reciprocals of the diagonal entries of the original matrix. So ano yung ibig kong sabihin? Kapag meron kang diagonal matrix D11, D22, D33, D44, hanggang and so on, tapos zero siya everywhere. Invertible yan palagi provided non-zero lahat ng entries dun sa main diagonal. Because it can easily be shown that the inverse of a diagonal matrix will simply be the diagonal matrix whose entries are the reciprocals of the original diagonal matrix. So ang inverse niya, marirase lang tong lahat sa -1. Because if you multiply my original diagonal matrix with this guy we have on the screen, makukuha niyo yung identity matrix pabalik. So kaya madali siyang i-test. So if your matrix A has non-zero diagonal entries, then the Jacobi method can properly be defined. Kasi nga, i-split ko siya, magkakaroon ako ng diagonal matrix D. Kapag walang zero dun sa main diagonal, then D qualifies as my choice for M because D then will be invertible. Tapos remember, ang splitting natin ay A equals M minus N. Tapos kinuha ko tapos alam natin si A ay equals D minus L minus U. So ibig sabihin, tapos ang decision natin, si M ay kunin to be equal to D. So N should be equal to L plus U. So for the Jacobi method, these are our choice of the splitting M comma N. And following our discussion about how to compute the matrix T and the vector C using the splitting, ito yung makikita natin. So yung transition matrix o yung iteration matrix para sa Jacobi method is simply M inverse times N. It's the inverse of the diagonal matrix times N, which is L plus U. And then the scaling vector is M inverse times B. So that's going to be D inverse times the vector B. And so we can now define the Jacobi iteration. The Jacobi iteration is this guy, okay? For some initial condition x upper 0, but that's fine because as long as the spectral radius of the Jacobi matrix T sub j is less than 1, then sure tayo nagko-converge to kahit ano pa yung starting condition na piliin natin. Okay? So this is the matrix form or the vectorial representation for the Jacobi method. And actually, mas madaling i-program ito kasi i-declare mo lang na si xi vector, si ti isang matrix, si ci vector, tapos pagawa mo lang to, mag-do while loop ka lang o kaya mag-for loop as k going from 1 to n, tapos may stopping criterion ka lamang. So at every iteration, nakukuha natin yung vectors. But if you're a fan of serialized computations, gusto mong makita paano nag-evolve yung mga entries ni X, pwede mong i-carry out ito, or pwede mong i-expand ito in terms of the entries of the vector X. So remember si vector X natin, ang laman niya ay si X1 upper K plus 1, second component niya ito, hanggang sa nth component niya. Alright? Pagka sinulat mo, lahat ng mga bagay-bagay dito as what? As yeah, in terms of serialized form, ito dapat yung makukuha mo. Yeah, I think I realized something is wrong with this formulation. This should be Let me double check the serialized computations. Dapat ito yata ay T. Huh. But let me check that. All right. So yung serialized form. I will verify this content. Kasi ang idea, yung equation 8.6b, dapat makuha ko um, by expanding this one. So no worries about this guy. Tama yan. Na-implement ko na yan. Ito yung ginamit ko dun sa examples. Ngayon, nagduda lang ako dito sa expansion na to. Kasi I'm now confused. Was A sub ij supposed to be the entries of the coefficient matrix A? Or was it supposed to be the entries of the iteration vector T? Okay? So I'm not sure about that, pero I'll update you via email later today kung ano nga ba dapat yung nandun. Aij ba na entries nung coefficient matrix A o siya ba ay entries nung iteration matrix T? Okay? Kasi nga naman, x sub j, naka-multiply siya with this guy, pero walang c dito nakasama, so baka na-factor siya, na-divide ng aii. Yeah, ayan, hindi na ako sure. Pero mukhang tama na sa coefficient matrix siya. Pero yeah, I'll think more on that later. But yeah, keep watch out for updates on that matter, right? Pero this is safe. Gamitin niyo yung vector representation. Okay? And that's the Jacobi method. So yun lamang yung ibibigay sa atin ng Jacobi method. Now to illustrate this problem, okay? Tingnan natin yung example 8.6. Meron ako ditong isang 3x3 matrix given sa equation 8.7. Tapos, i-implement natin yung Jacobi method with the L infinity norm. Kasi nga, walang in-specify dun sa derivation na norm kasi nga equivalent naman lahat ng norm sa isang finite dimensional vector space. So, ideally, kahit anong norm pa yung gamitin mo, okay lang. Tapos sabi, gumamit tayo ng relative jump-based stopping criterion ng epsilon ay 10 to the minus 8. Okay? So you can carry out the Jacobi method but by first finding out what's the iteration formula. Okay? So una natin gagawin, i-deconstruct natin si A into DLU. Okay? So kung mapapansin nyo, ito si A, kukunin ko yung diagonal part niya. Diagonal part niya, yung diagonal entries. So yun yung matrix A. 0 na siya sa labas ng main diagonal. Tapos si matrix L, siya yung lower triangular part. Dahil siya yung lower triangular part, 0 sa taas ng main diagonal, 0 sa lahat ng main diagonal, i-harvest ko lang yung entries mula dun sa lower part ng matrix A, pero babaliktarin ko yung sign kasi may negative na sa umpisa. Alright? That's why we got 3 here, a negative 1 here, and a negative 2 here compared to these entries over there. Okay? And then I'll do the same thing para naman sa upper triangular part. 0 main diagonal, 0 entries under the main diagonal. Harvest the negatives nung mga nandun sa upper part ng matrix A. Okay? Now you have your DLU decomposition or sort of splitting of the matrix D. Sabi sa Jacobi method, yung M natin ay si D. Tapos ang N natin ay si L plus U. So mako-compute natin yung iteration matrix. The iteration matrix again is just M inverse N. M inverse times N. Pa-compute nyo lang yan. Inverse ng diagonal times L plus U. Ito yung makukuha nyo na iteration matrix T. Tapos ang scaling vector natin ay ito. Alright? So I think it's pretty straightforward. So sabihan nyo lang ako kung meron kayong tanong kung paano nakuha yung mga matrices na yan. I suggest that you guys verify the solutions I have here. I have some results in here. Tapos if possible, paggawa nyo na lang kay MATLAB o kay Python. Anyway, ito naman ay iteration lamang ng matrix multiplication saka translation. Okay? Now a quick check. Magko-converge kaya itong Jacobi method natin para sa matrix dun sa example? Well, one way to find out is to compute the spectral ranges. Okay? Alam na natin yung matrix T, compute natin yung spectral ranges. Unfortunately, hindi ko kayo tinuruan kung paano mag-compute ng eigenvalues and I cannot assume that you know how to compute eigenvalues because that's in linear algebra. So, gamitin nyo na lang or hanapin nyo lang yung syntax kay MATLAB o kaya kay Python. Alright? So, in MATLAB, ang pinagawa ko sa kanya ay pinakompute ko yung eigenvalues ni T.
So, kay MATLAB kasi, ano nga yung syntax? I think IJ or IJ. Sige, i-double check ko. I-run ko yung MATLAB ko ngayon. Kaya naka-close pa siya. Maglo-load siya. Tapos, of T. So, itong syntax na to, eigs of T, will compute the eigenvalues ng matrix T. So, kukompute niya lahat ng, wala palang S. So, EIG lang. So, kukompute niya lahat ng eigenvalues ni T. So, usually kapag meron kang isang n by n matrix, meron siyang n eigenvalues. So, kay MATLAB, yung EIG of T, hahanapin niya lahat ng eigenvalues ng matrix T. Tapos, kukunin ko yung absolute value ng lahat ng yon. Ang syntax pagkuha ng absolute value ng isang vector ay abs lang. So, si IHT ay isang vector. Vector consisting all of the eigenvalues. Kukunin ko yung absolute value ng mga laman ng vectors. Tapos kukunin ko yung maximum nila. So if you put this into MATLAB, max ng abs ng IH of T, ibibigay niya yung spectral radius ng matrix T. So sabi sa akin ni MATLAB, yung matrix T mo na yan, ang spectral radius niya ay 0.51. And I'm quite happy about that because, okay, less than 1 yung kanyang spectral radius, so sure ako magko-converge yung iteration. At hindi lamang siya magko-converge. Magko-converge siya kahit ano pa yung initial condition na pipiliin ko. Alright? So I just wrote that here. So dahil magko-converge naman siya sa kahit na using any initial condition, so I'm gonna choose the origin as my initial vector. Okay? So bahala kayo pumili kung ano yung initial vector na pipiliin nyo kung di-specified siya kay problem. Tapos, ira-run ko na yung Jacobi iteration kasi alam ko na si T, alam ko na si C. Lagyan ko pala to ng subscript, TJ at saka CJ to differentiate it later with the transition matrix and the scaling and the translating vector sa Gauss-Seidel at saka sa SOR method. Okay? So, yun. Tapos, ito yung kanyang results. Medyo may problema lamang dun sa una. Ito yung problema sa pagpili kay 0, 0, 0 as your starting vector. Because we are doing relative jump criterion, right? So, ibig sabihin, ito ay mako-compute as yung norm. Sabi rito, gumamit tayo ng infinity norm. So, ito ay infinity norm ng x upper 1 minus x upper 2, x upper 0 all over the L infinity norm ng x upper 0. Pero ang norm ng zero vector, kahit anong norm ng zero vector ay equal kay 0. So, ito ay magzi-0. So, kung hindi nag-a-allow ng division by 0 yung inyong computing software, huwag kayong pumili ng 0, 0, 0 as your starting vector. Ang kagandahan kay MATLAB, alam niya na paano i-handle yan. Kapag ka nagpa-divide ng 0 yung user, gagawin niya lang infinity yung sagot. Alright, and then infinity is known by MATLAB to be greater than any number, so definitely this is still greater than the error tolerance 10 to the minus 8 that we set in the problem, so magko-continue siya dun sa susunod na iteration. Okay, so ito yung mga entries dun sa solution o dun sa estimate vector on the first iteration. Ito yung estimate natin para sa solution on the second iteration, and so on. And you see that it's quite it is quite slow because it took 29 iterations before we reached the stopping criterion 10 to the minus 8. But actually, we got a very good result here. Parang up to machine precision na nakuha niya yung exact solution. So, pero may mga decimal places pa yan after 2, 4, 6, after the 6th position after the decimal point, pero hindi siya napasama dun sa display ni MATLAB para sa akin. Okay? So, yeah, it is very close to the exact solution 1, negative 3, 4 transpose. Okay? Tapos, pag meron na kayong result, kailangan niyo yung i-analyze ng konti. So, paano natin yan i-analyze? Tingnan natin yung relative error. And then kapag kung ano yung ginamit nyo na norm doon sa relative jump, okay, pagko-compute ng relative jumps, okay? So, yun na rin yung gamitin nyo all throughout. Sa lahat ng i-measure nyo na norm, maging consistent tayo, right? So dahil L infinity norm yung ginamit dun sa relative jump, yung L infinity norm na rin yung gagamitin ko to measure the errors and to look for the asymptotic error constant. Okay? So yung relative error, kunin mo lang gaano kalayo yung actual solution mula dun sa estimate nating nakuha divided by the norm of the actual solution. So pag pinakompute ko kay MATLAB, this guy minus this guy, pinakompute ko yung size, gaano siya kalaki with respect to the L infinity norm, sabi ni MATLAB, it's about 9 times 10 to the minus 9. And the L infinity norm of X, madaling makompute yon kasi ang L infinity norm niya lang naman ay yung pinakamalaking absolute value. Ito yung entries ni X, pinakamalaking absolute value sa kanya ay si 4, so ang denominator ko ay 4. So essentially here we see that the relative error is about 2.33 times 10 to the negative 9. Okay? Tapos, pero sa totoong buhay, hindi natin usually alam ano yung exact solution. So kapag wala kayong information about the actual solution, what we can do as our estimate for the relative error ay ito. Gawin natin to. Compute natin itong value na ito. So I can consider AX star minus B to be the error. Bakit? Kasi remember, sinosolve natin yung AX equals B. So we want AX star to be as close as possible to B para maging totoo yung solution. Kasi pa-plug in ko dito si X star eh. So gusto ko yung AX star ay equal kay B talaga. So pwede nating masabi na yung discrepancy ay i-measure natin as the difference between the left-hand side of this guy and the right-hand side. So yun yung i-consider ko as the error vector kapag hindi ko alam yung actual solution. Tapos, i-divide ko yon by the norm of what value we are striving for. Remember that we are striving for AX star to be equal to B. So yung denominator ko dun sa relative error ay gagawin ko ay si B, ay yung magnitude ni B. Kasi nga gusto makita yung percentage. Gaano kalayo si AX star as a percentage of B. Alright? And in that case, we can assign our relative error to be 3.24 times 10 to the minus 9. Okay? That's not 10 to the minus 8 na stopping criterion, but that is to be expected because we know the convergence is linear. Okay? Tapos, gaano siya ka-linear, tingnan natin yung asymptotic error constant. And per the remark in the discussions above, the asymptotic error constant is not more than the operator norm of the iteration matrix. So ito naman, pinakompute ko lang to kay MATLAB, though may formula na tayong na-establish para sa L infinity norm ng isang matrix, pero hindi nyo siya kailangang ipagawa pa mano-mano gamit yung formula na binigay ko sa inyo earlier. So pwede nyo lang gawin kay MATLAB norm ng matrix T, tapos I and F. Kukomputin niya yung infinity norm ng iteration matrix T. Kasi sasabihin niya, ang sagot niya ay 0.778. So we know that the asymptotic error constant for the Jacobi implementation of this method is less than or equal to 0.778. Okay? You can try example 8.7, 4x4 matrix yan. Yeah, nandito yung solution, tapos i-verify nyo na lang siya. So I think the crucial part here is for you to design the iteration matrix. Kunin nyo si D, kunin nyo si L, at saka si U. Think of how you can implement that in MATLAB or in Python. Tapos after that, straightforward na. Kukomputin mo lang yung TJ, tapos yung CJ para ma-define mo yung iteration scheme. Tapos magpo-for loop ka lang or magdo-do while ka lang habang yung stopping criterion ay hindi pa nami-meet. Okay? Now, I don't have any more time to continue the discussion. Siguro last note na lang, when you're doing example 8.7, take note na ang pinagamit ko dito ay L2 norm. So, kailangan nyo ring palitan yung norm na ginamit. So, baka mag-panic kayo. Sumulat kayo ng program para sa example 8.6, tapos hindi nyo na-recreate yung solution na nakuha ko rito for 8.7. Okay? Posibleng error ay nakalimutan yung palitan yung norm. Etong mga relative jumps ay na-compute using the L2 norm, and all of the descriptions, the accuracy measure, the convergence measure, ay lahat in terms of the L2 norm. Pati yung estimate sa asymptotic error constant ay kinompute ko using the L2 norm. Okay? Now, ayoko nang mag-dwell masyado dun sa remainder nung ayoko nang pahabain pa yung discussion about iterative methods and let it spill over next week. Kasi gusto kong makaabot pa tayo sa exciting na parts ng ODEs, which is the next section. So, inisip ko, Inisip ko kung magdi-discuss na lang tayo sa lab sa Monday para i-present namin yung Gauss Seidel at saka yung successive over relaxation technique, or gawin na lang natin siya sa Wednesday. Inisip ko kakayanin ko ba sa Friday? Tapos iiksian ko na lang yung discussion sa Friday ng regularization techniques. What do you think, guys? Gusto niyo ba mag-discuss sa lab or wag na lang? Or wala kayong pake? Kung ano lang maisip pa. Sige, ganito na lang. So, hindi na... Sige, wala na lang discussion sa Monday lab. Pero kindly start... Pero sayang pala yung Monday. Sayang yung Monday. Alam ko na, ganito na lang. Sa Monday ay magdi-discuss na lang kami sa lab nung natitirang dalawang methods. Yung Gauss-Seidel at saka yung SOR method. Tapos ang deal na lang natin ay i-move ko yung deadline nung lab exer 3.2 papunta kailan? Papunta sa siguro Friday next week. Okay lang ba yun? React naman kayo, guys. Kung okay yun. Parang hindi okay sa inyo. Okay lang ba yun? Sige. Tapos para sa Monday, di-discuss namin itong Gauss-Seidel at saka SOR. Tapos kung meron kayong posibleng tanong sa implementation niya, pwede rin naming mabigay. Pwede kong i-flash yung MATLAB implementation ko nung tatlong methods na to sa discussion sa Monday. Yun yung hindi ko na kayang gawin sa lecture kasi 1 oras lang tayo nagdi-discuss, ano. Tapos matatapos siya. So sa Wednesday, ibibigay ko na lang yung Wednesday as a free time for you, yung 12 to 1 natin, para gumawa ng exercise. But I will open up MS Teams, itong meeting natin, para kung may tanong kayo. Alright? Para pag nagagawa kayo, may questions kayo about the implementation, I can address them on Wednesday. Tapos ang deadline ng pasahan niya would be Friday next week. Friday next week. And then on Friday, magdi-discuss ako ng isang regularization method, which is called the L-curve. Sana naman kaya ko siyang tapusin ng isang meeting lang yung L-curve. But I think that's better. Tapos, tanong ni Ezekiel kung papanoorin yung lab meeting sa D2L. Talagang ang galawan natin ngayon ay kung papanoorin, ano. Tatanong ko muna dun sa lab instructors kasi pwedeng kanya-kanya kaming labs, tapos lahat kami ay magdi-discuss. So kaya-kaya naman yan ng mga lab instructors nyo, ano. So mga naging estudyante ko rin sila. Naging estudyante ko nga ba sila? Yeah, naging estudyante ko sila. So marunong sila dapat nito. Kasi kung hindi, babawiin ko yung grade na binigay ko sa kanila nung araw. So yon, kanya-kanya na lang siguro. Or kung ayaw nila, kung mag-rally yung mga teachers nyo, kung mag-object sila, edi pwedeng sa D2L na lang kayo magpunta. Pero watch out for our announcement. Ano? Pero we will tentatively plan to meet the labs separately. Para rin mas intimate. Kung may questions kayo, pwedeng ma-address. Alright? Mas marami yung teachers na makakapag-address. Okay? So, yun. Tapos, ano pa ba? And then, on Friday, matatapos natin. So, probably Monday, okay? Monday, I can give you the problem set. Monday, week after next. Pwede kong mabigay yung problem set. So, kung ibibigay ko yung problem set natin, kasi tapos tayo ng Unit 3, ng Unit 2 sa Friday next week, pwede kong ibigay yung problem set ng, anong gusto nyo? Bigay ko na siya ng Friday night or antayin na lang natin yung Monday? Mag-work na ba kayo ng Saturday, Sunday? Or yung susunod na lang na, sige, pag-isipan ko. Titingnan ko yung schedule na pinakamaganda para sa inyo. Especially para dun sa mga nagwa 155 kasi problem set nila next week. So magsasabay nga ba? Yeah, let me see the schedules para kasi sabay matatapos yung mga units natin. Pero anyway, so let me think about that. Any questions, guys? Medyo feeling ko ang bilis ng discussion ko ng Jacobi at saka ng splitting methods. Okay, yeah, I'll take that into consideration, Charles. Yeah. Ganun ulit, tatlong modes ulit. Nasabi ko na naman yung computation part, crowd factorization, yung magiging computational part. So isip lang ako ng isang magandang linear system na ipapa-crowd factorization ko sa inyo. Yun yung reading assignment na binigay ko dun sa isang module. So simulan yun pag-isipan. Kasi kukunti pa lang naman yung gagawin natin. Pwede nga hindi pa kayo gumawa ng extra over the weekend or before Monday. So pag-isipan nyo kung paano ipaprogram yung crowd factorization. Mas maganda kung ipaprogram nyo siya sa MATLAB or sa Python kasi baka malaking system yung ibigay ko sa computational part. Kasi remember, ang ating objective ay to use the methods in a scientific problem. And most scientific problems are large in nature. So parang hindi masaya na mag 2x2, na mag 3x3 o 4x4 lang tayo sa problem set. So bibigyan ko uli kayo ng isang specific scenario na makikita niyo yung application ng numerical method. Number 1 is the usual essay. Number 3 would be computational part. Pinag-isipan, the objective part. Inisip ko pa nga kung kaya ko magpa-objective part eh. Siguro true or false na lang tapos fill in the blanks gamit yung mga formulas. Kaya lang limited ako kasi ang pwede ko lang paglaruan ay Gauss yung mga norms tapos yung estimates of the relaxation parameter and so on. Pero siguro maitatawid ko naman yun 4 or 5 questions, okay? So, yeah, sorry, overtime na ako. Super, ilan na? 13 minutes na. So, any last questions, concerns? Okay, afraid with a T si Charles dun sa coding part. Trust me, ang dali ng coding nito. So, kung meron pa rin kayong mga paghihinala, na mahirap yung coding, pag-usapan natin sa lab sa Monday, okay? So, I can demonstrate to you my code for this one, okay? Kasi simple talaga siya, yung coding niya, okay? Pero kailangan kong i-double check, nalito ako bigla dito. Nalito ako sa explicit form. Kung ano nga ba yung AIJs din. I think it is the entries of the matrix capital A. Pero, yeah, mukhang sure na ako. Siya ay kay capital A. Pero sige nga, i-recompute ko mamaya. Kasi kinopya ko dun sa libro. Medyo nagduda ako dun sa notations niya. Pero sige. Pero yeah, I hope the concept makes sense. Alright, so Tapos gawin niyo yung examples. Kung gusto niyo naman mag-advanced reading, magpabida, so basahin niyo na yung Gauss-Seidel at saka yung SOR method kasi related sila sa isa't isa. Then on Monday, we can see paano siya ini-implement. I'll probably demonstrate how I did it in MATLAB. Kasi super dali nga lang niya. Pagka vectorial form, kapag ka matrix form, medyo tricky. Kapag ka, lalo na sa Gauss-Seidel, kung gagamitin niyo yung explicit form. Sorry. Etong explicit form ng Gauss-Seidel. Mas madali pa rin yung iterative scheme niya na gagamitin mo ito. Okay? So, if there are no other concerns or questions, then enjoy the weekend, guys. You deserve it sa dami ng pinagdaanan nyo itong linggong ito. So, unfortunately, May 1st fell on a Sunday, so wala tayong long weekend. But sulitin nyo na kasi alam ko, Mayo na. So, napakaraming mga requirements. Tapos medyo anxious pa tayong lahat. Hindi natin alam kung anong mangyayari sa Pilipinas in the next 2 weeks. So let's see. So, but yeah, try to get some rest and then let's see each other again. D2L on Monday and everyone else on Wednesday. Bye, guys.